We're going to continue to talk about correlation today. So when we were talking about the scatter plots and describing the association yesterday, we discussed the fact that the relationship does not change no matter what units we have. So because the units don't matter, we can remove them altogether. The only way in statistics to get rid of the units is to standardize the data. So that's what we do. When we standardize the data, both variables become z-scores. So you have your z-scores of your x and your z-scores of your y. So the coordinate points become z-score x, z-score y. On the right, we have a scatter plot of the standardized weights and heights. And when we standardize the data values, we're actually able to see that the underlying pattern appears to be more steep. And we can see this because our scales are now the same. We now can keep things on the same scale, which makes seeing the pattern a lot easier. And it also gives us a better idea of the actual strength. Continuing with correlation, the scatter plot now has green, red, and blue dots. So our correlation will measure the strength as well as the direction. So when we standardize our data values, we can see which points give a positive association, and those would be the points in green. And then we can see which points give a negative association, which are the points in red. And then which points don't have an effect on the correlation, which are the points in blue. What we can see here is that there are very clearly more green points than red points, so our correlation is going to be positive, but it's those red points that weaken the positive correlation and cause it not to be exactly 1. So what does this really mean? Well, it gives us a correlation coefficient, which is a great value. It's a numerical measurement that gives the strength and direction for a linear relationship. Again, I emphasize that the data has to be linear. It can be calculated using the equation in red, but we're going to do it on our calculator instead of using this formula, but if you are concerned, you will be given that formula on the AP test. So more about the correlation coefficient. It is a number between -1 and 1, and again it tells you how strong the correlation is. It also tells you the direction, so if it is negative, your direction is negative and have a negative association. If it is positive, the association is positive and the direction is positive. The closer to 1, the stronger the association is, or the closer to -1. Again, the sign is just showing the direction, so it's the magnitude of the number, or the absolute value of the number, that tells you how strong it is. So there are some conditions that we have to make sure are met before we can decide to use the correlation coefficient. You must check these 3 conditions. We'll have to check conditions all year long, so it's good to get into the habit of making sure that you're checking them now because it will be an absolute necessity later on. So the first condition is the quantitative variable condition. So you have to make sure that both of the variables are quantitative, meaning that both variables have units. Then there's the straight enough condition. The straight enough condition is pretty straightforward. You need to make sure that the data is straight so that there is a linear association. And then the last one is the outlier condition, which basically says that outliers can have a large effect on correlation, and therefore we have to actually calculate the correlation both with and without the outlier. Correlation properties. So the biggest property is that correlation is not cause and effect. I want you to repeat after me. So talk to your laptop, talk to your computer, talk to your iPad, whatever you're using, and say, correlation is not causation. Say it again. Correlation is not causation. Just because 2 variables have a relationship does not mean that one variable causes the other variable. There are often underlying variables that are involved in that correlation. And those variables are often the reason why a strong correlation may not be exactly 1. So, for example, when you're selling a car, the age of the car has a huge effect on the cost of the car. It is a linear relationship. It's negative because as the age of the car increases, the price decreases. And it's going to have a strong relationship. So correlation is going to be pretty close to 1. But there are other factors involved when you're looking at the price of a car. The condition it's in, has it been in accidents, the number of miles, the features it has, among other things. So there's always other reasons that have an effect on something. So again, correlation is not causation. In a nutshell about correlation, the sign is going to tell you the direction. Correlation is always going to be between -1 and 1. So if you have a value outside of that range, it's not right. And then the correlation is not affected by changing units because it's based off of z-scores. And again, it's because the relationship doesn't change no matter what units you're using. Therefore, your correlation coefficient has no units. So if somebody says that your correlation coefficient R is 0.98 miles per hour, they're wrong because there's no units. It also measures the strength of a linear association. Again, linear being key. It only works if your scatter plot is straight. And it's also sensitive to outliers. So if you are finding the correlation coefficient, you have to find it with and without the outliers. Correlation tables are an effective way to show the correlation between multiple variables. So if you're looking at the relationship among a lot of variables, correlation tables can be really helpful. The rows and columns give the name of the variables and the cells hold the correlations. And again, it's effective for looking at large sets of data. So for example, here we have a correlation table. The diagonal is always going to be 1 because you're comparing a variable to itself, but you can just quickly easily see that cash flow and profits have a strong correlation, whereas cash flow and assets, not as strong of a correlation. So it just allows you to see maybe what the relationships are right away. Okay, straightening scatter plots. We're going to spend a lot more time on this in chapter 10, but I want to kind of introduce it right now, just as a quick introduction. So because we can only use correlation for straight lines, when the relationship shows a bent or slight curved relationship, we can often straighten that relationship by re-expressing one or both of the variables. And when I say re-expressing, we're really doing some type of mathematical manipulation to the variables. For example, when comparing the shutter speed and f-stop on a camera, we get the following values. So SS is shutter speed and F is your f-stop, and it gives this scatter plot, which shows a slight curve. It's curving upward. So we couldn't use our correlation coefficient because we don't have straight data here. So if we re-express it by squaring the f-stop, and that's shown right here, the fact that it's squared, we end up with a much straighter scatter plot. And that's what our goal is. We want to take a slight curve and make it straight. So in that example, we squared the f-stop and ended up with a more linear line. So in the first graph, our correlation coefficient was 0.979, which is still really strong. But when we straightened it, we ended up with a 0.998, which is much stronger, much closer to 1. The increase is good. We want to see that correlation coefficient increase. But the most important thing is what we saw in the scatter plot and the fact that the shape now is linear, so it's actually appropriate to use the correlation. Okay, so that's it for today, and that's it for chapter 7. I will see you guys tomorrow. Have a good night.